Hey everyone, Morgan here. So we're going to be talking about half-life today, and we're going to actually do some algebra to prove the formulas that were presented to you on page number 5. So I'm pretty sure you understand the concept of half-life. I'm going to use a graph in addition to a definition. The definition is basically just the amount of time required for 1/2 of a sample to react. The amount of time required for 1/2 of a sample to react. So we plot concentration versus time, and we get a curve that looks somewhat like this. Now, if this is, call it concentration of A, and we cut that in half, draw this over, draw that down, this amount of time should be the half-life, T1/2. Now that's A over 2. Now if we cut that in half, A over 4, and we do the same thing, this should be the same amount of time as this was. Okay, and it's pretty close the way I've drawn it. All right, now we're going to look at first, second, and 0th order reactions to see how this works. So what I know about a first order reaction is that the natural log of A equals minus KT plus the natural log of the original concentration of A. Now at the half-life, at T1/2, the concentration of A is equal to 1/2 of A naught. So let's do some plugging and chugging here. A little bit of grouping like terms, ln of A minus ln of A naught equals minus KT. Using a little bit from math analysis, the ln of A divided by A naught is equivalent to that term equals minus KT. Then what I'm going to do is actually invert these. And that's going to make it the negative, which will cancel out my negative sign on the other side. So I now have the ln of A naught over A equals positive KT. So plugging this in, the ln of A naught over 1/2 of A naught equals K, and we'll call this T1/2. Well, the A naughts cancel, so I have the ln of 2 equals K T1/2, or that the half-life, T1/2, is equal to 0.693 over K, and 0.693 is the numeric value for the ln of 2. And that matches that first equation we gave for half-life back on page 5. Now, in a second order, 1 over A equals KT plus 1 over A naught. That is the integrated rate law for a second order reaction. So 1 over A minus 1 over A naught equals KT. A after a half-life is 1/2 of A naught. So 1 over 1/2 of A naught minus 1 over A naught equals K T1/2. This is like saying 2 over A naught minus 1 over A naught, which is going to be equal to 1 over A naught. Is equal to K T1/2, or that the half-life equals 1 divided by K times A naught. Now what this shows you is that the half-life of a first-order reaction does not depend on the concentration of the reactants, but the half-life of a second order does. And it will for a zeroth order also, where the concentration of A equals minus KT plus the concentration of A naught, or the concentration of A minus A naught equals negative KT. 1/2 of A naught minus A naught equals minus KT 1/2. So this should be negative 1/2 A naught equals negative KT 1/2. The minuses cancel, okay? And then I can solve for T 1/2. It equals the concentration of A naught over 2K. All right. Now there's going to be a lot of implications for this equation. Over here, there are two equations that are very useful. This one and this one. We're going to use them a lot on the next page. Now this one you're familiar with from your math analysis book. A equals A naught e to the minus KT. It's the same equation, just presented a little bit differently. Okay, that's it for page 6. Hope you're having a good day. This is Morgan signing off.